Hello, and welcome back to Collaboratory. Here I have the previous code that we worked out in part A, and let's get started with part B. So we are given the same situation, however, a little bit has changed. We are given to calculate the response of the system if the flow rates are changed to 0.55, 0.28, and 0.6 meters cubed per second, respectively. So with that being said, let's go ahead and get started. The first thing we want to do is we want to import our make subplots, as we will be at the end of this we will be looking at the three plots subjectively and see how they correlate with time. So from plotly.subplots import make subplots. It's easy. Right. And then I'm going to go ahead and take this out. You go ahead and put this back in here. And we can go ahead and put our new values for our qn, right? So qn2 is now going to be an array of, we said 0.55, 0.27, and 0.6, I believe. 0.28. 0.6, sweet. And then for our CA in2, we are just going to keep what we had up here. So we're going to call the copy function. So we're going to call our first values, and we're just going to do dot copy, parentheses open, oops, not like that. And then we'll do the same thing for our tn. Right, so this is tn not dot copy, and we have our new values for these in there. And then we also want to put our value for, I'm just going to put it back here, I guess, tn, that is going to be 100. Right? Or I think that's 1,000, I believe, sorry. Or no, yeah, 100, sorry. So that being said, we can go ahead and recall our solve IVP function so we can get our new values for that, right? So I'm just going to call this result2. Yeah. And that is going to be equal to solve IVP. And then we're going to be using lambda again, but with the t vector as well, or the time as well. And then again, our right hand side, but we're going to be using t, v, and then our new value. So qn2, ca n2, and tn2, right? And then we want our t-span, which is 0 to t-end, right? And of course, our why not is just going to be Paulo, right? Our solution, right? And then method, we want the Radeau method to be using. And then, of course, we want our dense output to be true so that we can dense output to be true, so that we can go ahead and integrate this out. Okay. So now let's go ahead. We can go ahead and start plotting. So I'm gonna do mp dot linear space. Right. I'm gonna do 0 to t end, and we're gonna have 500 points. Right. Then so we can do unpack this and put h plot, our CA plot, and our T plot all equal to I think it's res 2 dot what is it again? Oh, yes, so it's res2 dot follow at t-plot, right? No, I think this is res2 dot solve. Yeah, okay. Sorry. So now we can go ahead and plot these things out, right? Oh yeah, because I have to make this. Right. Okay. now it knows what t-plot is. Okay, now we can do fig1 dot add or make subplots. Wait, no, sorry. Let's run this out. And then we have fig1 equal make subplots. We're going to have one row, but we have 3 columns, right? Because we're going to have 3 different graphs. Fig1 dot add scatter. Right? We want row to be 1, column to be 1 as well. And then our x-axis is going to be our t-plot, and our y-axis, we're going to make this h-plot, right? That's going to be the first one. And then we can go ahead and give it a name. That's simply going to be h, which is height of fluid in tank, and meters, right? What we can do is go ahead and copy this out just for time's sake. We're going to change these to second column, third column, then these plots are CA plot and T plot, and then these names obviously are different. This is the concentration of A, and this is the temperature in Kelvin. And shift enter, we should get our 3 graphs. Beautiful. So as you can see, we're given it 3 graphs. This is the height of the tank, this is the concentration of A, and the temperature of Kelvin. So you can see these roughly stabilize out around 50 and push through. And for the height of the tank, see starts off at 10 and rounds off around 10.4, around 70 to 80 seconds. And you can see that temperature goes through a similar path or similar idea where it starts off low and it increases up to 81.25 around 50 seconds and stays out that way, while the concentration of A is inversely related to the two, as it starts off high and it goes down low and stabilizes at about 0.4 for the concentration. So with that being said, there is the second part of this homework series. Hope you guys enjoyed, and I'll see you guys in the next one.